through engineering innovation. They worked together through their semesters-long class to come up with an idea for GAIA, a sustainable engineering competition that focused on allowing college students to create long-term tangible impact with engineering designs and would allow them to continue to make the same impact for years to come, continuing on their project. They saw a hole in the market for the competition, for competitions and challenges where teams maintain their presence in a community that they have attempted to help, adjusting their designs to better meet community needs after they've been implemented. So GAIA decided to fill that gap. So Becca, Mark, and Mohammed worked alone for the first semester and a half, creating our website, coming up with our long-term goals and plans, finding our community partner WindAid, and creating an organization from the ground up. And then in November of 2022, they recruited their first new class of GAIA organizers. Those are some of the photos of the organizers that are still here today. So we have Anna, our chief marketing officer, Sophia, one of our marketing sub-team members. Up there in the corner is AJ, who you'll be hearing a presentation from later today. And then I'm also down there. And yeah. And then that was the mission statement that we created, which we like to often reiterate in our team meetings, that GAIA is a national competition that empowers college teams to conceive, design, prototype, and execute high-impact solutions for global sustainability. And at this point, I would be remiss if I didn't take a further look into our community partner, WindAid. The WindAid Institute is a nonprofit based in Trujillo, Peru. WindAid provides rural electrification to the countryside of Peru by building wind turbines from scratch. We chose to partner with WindAid not only for their superb work for the people of Peru, but their similar values to GAIA about the importance of providing students the opportunity to create hands-on impact. WindAid operates on a model of allowing students to come to their workshop to build these turbines and implement them in the community. They sponsor cohorts of students to come stay in Trujillo for 4 weeks while gaining technical, hands-on experience in their workshop and traveling to the rural community to see the impact they make on the lives of the local Peruvians. As with any new organization, the first year of GAIA had some bumps in the roads, but was highlighted by the successful work of our first team, the British University in Egypt. Although they did not field a team to compete this year, they did actively participate in our competition the first year of GAIA and allowed us to gain an understanding of how we wanted our second year as an organization to play out. In our first year as organizers, we figured out how we wanted GAIA to look both internally and externally. We learned how to work together, and our founders learned how to lead a team of 20 people working together to achieve one shared goal. This year, we recruited the majority of our team members with some notable faces like the head of our business team, Sunny, and the head of our international team, Kylie. We re-upped our partnership with WindAid for another incredible year of working together, and we worked on our long-term goals for GAIA and decided to focus on a rebuilding year. All the while, we were planning our first trip to Peru to visit our community partner, WindAid. These are some photos of our team this year. Yeah. And then over winter break this year, GAIA achieved our first major milestone, winning a 5K grant that allowed us to send 3 Cornellians, including one of our original founders, Mark, to Trujillo, Peru to do research for our problem statement, scope out the WindAid site, and build a turbine for our partner community. It was a really valuable trip for us because we were able to gain face-to-face connection with our community partner and meet the organizer of WindAid that we had been interfacing with for the past 2 years, Gandhi. And then this is like a photo from the site, and then that's them holding a GAIA banner down at the workshop. And now we have reached today. We're at our first scale in-person demo day. This has been a long time coming for us organizers, and we could not be more thrilled to be here today. Thank you to the GAIA organizers who made this possible, the ELP team of Miriam, Rob, and Erica, and of course, the competitors. We're so excited to hear about the solution you've created for this year's problem statement. That's it.
Hello, I am Becca, and I am the technical lead of GAIA, as well as one of the original co-founders. And I'm going to share a brief presentation about the more technical side of GAIA. This will still not be a technical presentation, but it will be an overview of what the technical team does. So I'll be talking about the problem statement, which the technical team is responsible for writing. The trip to Peru that we recently executed in January, the generator modeling project, which the GAIA organizers technical team took on as part of our scope this year, and then also looking forwards towards the future of the technical side of GAIA. So GAIA was started with a mission of impact, and we were searching for a way to define impact in a way that can be measured and therefore used as engineering goals. And a great example that we drew from heavily of this is the United Nations Sustainable Development Goals. If you aren't familiar with them, these are 17 goals that were created in 2015 by the United Nations and are set with a goal completion date of 2030. And they include all of the goals that you see here. And for GAIA's first problem statement, we are focusing specifically on goal number 7, which is affordable and clean energy for all. And to achieve that goal, we have partnered with the WindAid Institute, a NGO or non-governmental organization based in Trujillo, Peru. And WindAid's goal is to create and install locally manufactured small wind turbines. And this is for the purpose of rural electrification for households who otherwise do not have any access to electricity. And specifically, WindAid has a design that they have been working with for years of their turbine. It's about 200 watts, enough to light a couple of light bulbs in the household. And the main challenge that they're facing is that this design is still expensive. And so we are working with them as GAIA to help innovate on the design to reduce the cost. And the design of the WindAid turbine is inspired heavily from a design by someone named Hugh Pigott from the United Kingdom, who has done a lot of work with locally manufactured small wind turbines all over, and especially in Latin America. And based on our discussions with WindAid, the biggest area of cost concern for them right now is their controller. The controller is a part that cannot be locally sourced from Peru. The only part of the turbine that is the case for. And so they currently import their controller from a company in China, and the controller itself costs $100, but there's an additional $200 of shipping and tariffs and import taxes on that. And that's like a pretty major part of the overall turbine cost. And so that is why the problem statement this year is focusing on how can we reduce the cost of the controller. And so diving into the problem statement, this is a document that the GAIA technical team creates each year to guide the competitors who are entering with engineering functional requirements, design requirements, optimization objectives, and a wealth of technical resources and information. And so we created the objectives working closely with WindAid about what would be most impactful for them. And so that is why the emphasis is more on cost reduction than it is on power improvement, because there is not going to be that much benefit to a small amount of power increase, whereas there would be a lot more benefit to cost reduction because it would enable WindAid to make more turbines and give more people access to electricity who do not have it. And the requirements are derived both from physical constraints regarding the governing laws of all the subsystems, as well as the operational constraints and the operating environment. the operating environment of Peru in an outdoors location and needing to survive for many years. And the requirements also specifies subsystem interfaces between the different components. And finally, the problem statement contains a compendium of resources intended to help teams get started, both introductory and complex detailed technical modeling. And we also included a week-by-week timeline. And so this is a screenshot of the part of the design requirements portion of our problem statement. And so you can see that the electronic system was required because it was the main focus of wind aid for cost reduction, with optional subsystems of the blades and the generator, and several representative design and functional requirements. And additionally, this is the part of the technical resources spreadsheet that we compiled to have all the information in a centralized location, sorted by subsystem, and easily searchable to increase the access to information and hopefully enable even first-time teams who have never worked with wind turbines before to be able to get up to speed. And so this problem statement represents phase 1 of the entire GAIA program. But the GAIA program has 3 total phases. This first phase is the prototype phase. It's a design, prototype, and test phase running through the school year, basically from September, culminating in this event in April. And that phase is with the goal of innovating on the design, exploring, and testing the proof of concept. The second phase is the pilot phase, or the implementation phase. This happens in the summer, and you'll hear more about that later on for sure. This summer in August will be the implementation phase, where the entrants actually travel to Peru and implement their design. And the third phase of GAIA, which we have not yet realized yet with this inaugural cohort, but where we eventually hope to get to, is scale, where year after year, the engineers can iterate on their design with continuous improvement, do monitoring and maintenance work of the turbine, and most importantly, scale the solution to have a broader reach and ultimately to produce more impact, which is what GAIA is all about. And so I will next talk about some highlights from the trip to Peru that GAIA did a couple of months ago in January. This was a scoping trip to help gain information about the wind turbine and inform the problem statement. And so here's the picture again that you saw earlier of the GAIA team with Gandhi, who is the executive director of Wind Aid Institute. Some objectives of the January Peru trip are listed here. We are wanting to get data for both the wind aid generator and an alternate generator design that we call the Laplace generator, that another organization was working with Wind Aid to develop. Basically to get data for the two of them and compare them and determine the advantages and disadvantages of each. And then objectives 3 and 4 were about understanding the constraints that are relevant in Peru. And so the constraints related to the current manufacturing and maintenance process so that they can be improved with very specific recommendations in the problem statement, and also to understand supply chain, especially for electronics, as the electronics are the main pieces that could not be locally sourced for the wind aid turbine so far. And then fifth, understanding the context with the ultimate end users and understanding its role in the community for better user-centered design. And then finally, a reach goal was to also get data for the blades of the turbine. And so that was our schedule. And great, this is playing. So here is a video of the generator dynamometer system running. And so I'll point out each of these components. The green machine is an induction motor that we are powering from wall power and using to spin the white machine, which is the Laplace generator in this case. And this is called a dynamometer, and that's how we aimed to load the generator in order to collect data. And the Laplace generator would then be hooked up to the controller that we're also testing. And so, as I mentioned, another goal of this trip was to do some electronic supply chain scoping. Here's a picture from YMYS Electronics Store in Trujillo. This is one of the electronic stores that our team went to get an idea of their inventory, the kinds of components that were available and the kinds of components that were not available. And so this was really helpful to see that sort of like commodity components like these buttons and switches are quite available, but you won't necessarily be able to find something with a specific part number or very specific specifications, as well as understanding the sensors that are available. And so we detailed all of the findings from this January Peru trip in a report to give to WindAid, and that will serve as documentation for ourselves as well as other people who work with WindAid in the future. And so the accomplishments, as I mentioned, being able to better understand the supply chain, getting some valuable generator data, although we were not able to get all the generator data that we were hoping for. And so that would be a future plan. And you can hear more about that in the generator technical presentation, as well as we did not have the opportunity to gather blade data for the aerodynamics. All right, so I'll move on to generator modeling. This is another separate function that the technical team of the GAIA organizers works on. This was originally a portion of the problem statement for an additional team, but that team ended up not being able to participate this year. And so in order to try to still have the most positive impact that we can for WindAid, our technical team is also taking on this modeling project. And so the reason that we want to do modeling of the generator is that a previous master's thesis has done a pretty thorough analysis of the WindAid aerodynamics and the blades, finding that they are pretty near to optimal, and they can produce more than 500 watts of mechanical power. But on the other hand, the actual WindAid turbine is only producing a maximum of 240 watts of electrical power. And so that's less than half. And so you can see that the WindAid generator is quite unoptimized. It's not very efficient from a power perspective. And also it is rather expensive, costing more than $250. And so the objective would be to model the operation of the generator so that we can improve the power as well as the cost. And this will help, especially by reducing the cost, be able to bring WindAid turbines to more people in Peru. And so moving on to the next steps, another aspect of the technical team in the future will be to create a systems model. This will help to unify all the different subsystems and will be used in our problem statement in future years as the direct measure of impact. That basically, by including a physics model that has aerodynamics, the generator, the controller, and the battery, and the objective that we model is to minimize the number of hours in a year where the battery has run out of charge, and therefore the households do not have access to that electricity. That is a very a metric that aligns very well with the direct impact on people and their quality of life. And so this is why it's really important for us to make this systems model to be able to say how much an impact on an individual subsystem level will impact the overall goal of helping people have access to electricity who otherwise would not. And thank you. I'll open it up to any questions.
Hello, my name is Matteo Banducci, and I'm here to speak on behalf of the Cornell competitive team, comprised of myself, Chris Biloski, Nico Litt, Iris Wren, and Alyssa Shu. For our goal, we focused on the controller aspect of the wind turbine. Currently, as Becca mentioned earlier, it's super expensive and can't be sourced locally. So for our project, we focused on finding local components in Peru, which makes it cheaper for the user, easier to replace, and no transportation fees such as shipping and other international shipping taxes. Of course, this controller has to be equally effective while also maintaining it at a lower cost, or else it would kind of defeat the purpose of it. One of the challenges we had was creating a prototype to test in Ithaca to gain data and see how well our cheaper proposed design worked compared to their current, more expensive wind controller design. This involved creating a wind turbine simulation, which you guys will see later, and as well as ordering components to simulate our design, such as the generator, a motor, controller, dump load resistor, and rectifier. We also had to collect data to gauge the effectiveness of our design to see if it would help improve as well as cut costs. Our proposed design features a locally sourced solar controller with a dump load resistor to regulate the amount of power allowed to go into the battery. On the right-hand side, we have our prototype featuring the generator, rectifier, controller, dump load resistor, and battery. The rectifier is used to convert the generator's three-phase AC current into DC current. The solar controller is used because it regulates the amount of power allowed to go into the battery. The dump load resistor is used to dissipate the extra power from the generator, and it's dissipated into heat. And the battery was used just to store the energy we collected. As you can see on our proposed benefits, our proposed cost is more than $200 cheaper than the current cost because we don't have to worry about controller transportation, taxes, and shipping. Some of the obstacles we faced was creating the test setup. Obviously, we don't have a wind turbine here, so what we ended up doing was using a drill to simulate the spinning wind turbine to power the generator we purchased, as well as we had to find similar components to the ones that are locally sourced in Peru to see how effective they were relative to the current design in Peru. We also had to figure out how to rectify the three-phase AC current using multiple solar controllers, essentially replicating a three-phase rectifier. Some of the risks we encountered was the dump load resistor produces a lot of heat, so keeping it away from other lab equipment so it's not dangerous and also not hurting anyone, as well as our design is made up of several components, which means there's lots of wires and kind of poses a risk to short the circuit.
Thank you. So now I will pull up the longer technical presentation.
Hi, we are the Cornell team and specifically we are in charge of the technical presentation, which will give us more detail from the technical part and more expand on what the Matteo already presented us. And then first we will give us overview of what kind of things we are gonna cover for this presentation. First part is developing models, which is conceptually introduce what our circuit is composed of, and then what kind of specs we have or what we found from like the local sources at Peru and how it's possibly worked. And then we will give a very detailed calculation to prove this is actually work. And then we have this our physical circuit right now here, and we will give a short demo later. First part is like the conceptual design. For this like wind turbine system, we would definitely would like to find a wind turbine charge controller, because this wind turbine charge controller is like originally designed to fit the wind turbine system. However, its characteristic is like it is able to handle large fluctuation, which is a tremendous characteristic in like wind turbine, because like it can vary differently based on like weather and also the geological location and also many environment conditions. So it's like a perfect match. However, as we talked about before, we don't have this like local sourcing in Peru, and also the price just get pretty high when we get this source internationally because of like international shipment else. So what we are trying to do here is like to find a alternative, which is a solar panel charger controller. And the problem with this alternative is like it cannot like handle large fluctuation as well as like wind turbine controller. And also it doesn't have the built-in dimensions load. But it's a alternative we can find and prove with also like cheaper price. So we are definitely gonna dig deeper on how to fix this potential problem with this alternative later. And specifically, we are focusing on the MPPT solar charge controller, which could potentially handle the small wind turbine, and it can handle the range of the rated power and voltage. And in terms of the MPPT solar charge controller, it means like maximum power point tracking controllers. And it can continuously monitor the solar power's output, voltage, and current. And it actually works better than another option we actually research about, which is the pulse-wise modulation controllers. The modulation controller will actually try to make the voltage at a constant rate. However, the problem with this kind of stability is like the actual voltage it's using is pretty low, which means it's actually not that efficient. So our MPPT solar charge controller have like a better efficiency, and also like it means a shorter charge time. And this is like the MPPT is like have its like algorithm to adjust to different solar like I don't know, like solar input. So it's like it can optimal its power output based on the what kind of like solar energy it can receive. And this is like specific spec, which we'll definitely digger later for the our component spec parts. Yeah. And this is specifically the part the MPPT controller we find. And also another part beside the solar controller we need to consider to make this circuit work is we have like the rectifier and also the dump load resistor and the battery, as Matteo has already covered. So yeah, and this is like the proposed model. We have the generator connected with the rectifier and controller and battery. We'll definitely have like a better sense of like how it works later in our live demo.
So for the component compatibility, our first step here was determining the specifications of components, basically making sure everything matches together. So for after we had the controller, the next part we had to look at was the rectifier. The purpose of the rectifier is to convert the generator's three-phase AC current into DC current. There's two types, the passive and active. With passive rectification, diodes are used. They act like one-way switches, allowing current to flow in one direction. Passive rectifier is pretty straightforward because it directly controls the current via load impedance, and it doesn't actively adjust current flow. On the other hand, active rectification uses operational amplifiers along with transistors as controllable switches. The advantage of active rectification is the ability to actively control the current by adjusting the pulse width modulation setting. This provides more flexibility and efficiency in managing the output, especially under varying load conditions, as you would see in a wind turbine. So we had several choices when choosing rectifier. First off, the current. Second off, passive versus active. So our turbine, or in this case, the generator, only outputs three-phase AC current. So we're left with these two. And then the main difference here, passive versus active, is cost and simplicity. Passive is much cheaper, as with active, we'd have to use 3 single-phase rectifiers to achieve what would be achieved with just 1 triple-phase passive. Okay, so the rectifier we selected converts three-phase AC to DC via a full bridge. Given that a rectifier is going to be connected directly to the turbine, in this case the generator, we decided to use a model with a very high maximum input or output. We have 1600 volts. Additionally, when a rectifier rectifies, the three-phase AC currents are combined, resulting in a larger DC current, hence why we have 100 amp. As for the battery, we found this 10 amp hour lithium iron phosphate battery. It operates at 12.8 volts with a maximum of 14.6 volts. For comparison, the controller maxes out at 14.8 volts. This means that our components should be operating within the same range, once again, making sure everything's compatible. Additionally, this battery has a 10 amp battery management system. That means that it'll continuously supply 10 amps of current and should help stabilize the circuit and protect the battery, especially in the event of a power fluctuation. As for the dump load resistor, a dump load or diversion load resistor is used to divert electricity away from the battery once the battery is fully charged and dissipate it as heat. It's basically like a safety mechanism used to protect the battery from overcharging. So we selected this resistor for several reasons. First, it operates at 12 volts, or it also has a 24 volt option, but this one operates at 12 volts, just like much of our other components. As for resistance and power, we calculated our ideal values and selected a model with values most similar. And finally, this dump load is compatible with our MPPT controller. So for the purposes of testing, we needed a generator that we could spin to imitate that of the wind turbine. That being said, given that we had similar goals to Windade, we wanted our generator to be similar. As you can see, both our generators output a three-phase AC with 12 volts and operate at 200 watts. However, where we differ is in efficiency and rotation speed. Our generator spins at a max of 750 RPM and they're at 600, so we're getting more cycles in. Our generator is 85% efficient, whereas theirs is only 50%. So we're harnessing more energy off each cycle, meaning we should be collecting more energy overall.
Moving on to some of the calculations. So as Chris was saying earlier, we looked into the electrical frequency of the generator because the electrical frequency measures how fast, kind of how many cycles there are in the sine wave curve on a voltage versus time graph. So basically when the electrical frequency is higher, that means there's more cycles per second. So then the voltage will be switching directions faster. And then so when the voltage switches directions, the diodes in the rectifier experience what's called like a reverse recovery process. So basically they will still be conducting for a bit before dying off. And this could lead to some like power losses in the rectifier. So one other thing we'll talk about later is the voltage considerations for the generator, because although it's rated at 12 volts, depending on how fast you spin the generator, it could actually output like really high range, really drastic ranges. So we want to find the voltage and then determine the corresponding rotor speeds that we want to limit ourselves to when spinning the generator so that we don't, overvolt or undervolt the controller. But first, looking at the electrical frequency, as Chris was saying earlier, we found we used the equation of electrical frequency being equal to the rotor speed times the number of magnets. So for the wind generator, we found this to be 4,800 RPM, and testing generator was 9,000 RPM. So we can conclude that when we're spinning both generators at the same speeds, the efficiency in the rectifier would be a little lower in the testing generator than the actual wind generator. So then when we're actually observing efficiency in the wind generator, when used with the control rectifier, we may notice a greater efficiency than what we see here. And then now it's just finding the limits of how much volts we should produce in the generator and rotor speeds we should spin it at to produce that. So yeah, basically what I said. There we go. So first, one consideration we need to have when finding the output voltage on the generator is to note that it's not actually exactly equal to the amount of voltage that will go into the charge controller. And this is due to the rectifier in between the two. So when the rectifier rectifies three-phase AC current to DC current, the actual DC current will be larger by a factor of the square root of 3. So any voltage that we want to put into the charge controller should be divided by a square root of 3 to find the actual like output voltage we want from the generator. So this is the formula on the bottom in the conclusion that we found. And then so we calculated the output voltage, the max output voltage we want on the generator, given that our controller can take at max 65 volts, so we don't want to go over that, otherwise the charge controller will be fried. But so then we used the equation, we calculated, we found that the generator output voltage should not exceed 37.5 volts of AC at its peak. And then we did the same thing for the minimum voltage. The charge controller can take on minimum 12 volts, although we have to do some testing later to verify that the controller could just take 12 volts at minimum and didn't boost like lower voltage levels. And then we found that the minimum requirement is 6.93 volts of AC. So our range is from around 7 volts to 38 volts on the testing generator. And then so now that we found the range of voltages for our testing generator, we can find the rotor speed. So we use the relationship, proportional relationship of voltage output to rotor speed. And the constant that relates them is the back EMF, and it determines how much voltage you can produce per unit of speed you spin on the generator rotor. So for the testing generator, we were given what we assume to be a specific data point. So we were given that the generator produces 200 watts at rotor speed 700 RPM and produces 12 volts of AC current. So some assumptions we made were that this power is the max amount of power that the rotor speed can also produce at its max kind of greatest speed before the power drop off. And then we also assumed that the voltage of AC that we produced was at its peak, was referring to its peak voltage. And later through testing, we also found evidence that supported this within 20% range in calculations for the back EMF constant, which we found here. So given our rotor speed and the voltage, we found the back EMF constant to be 0.016. And then we used, now that we had kind of like, let me actually show the graph first. So we were given this specific point. We used it to find the slope of the voltage versus rotor speed graph. And so now given any voltage output, we can now find the speed to spin the rotor. And then the formula is on the bottom right there. Rotor speed equals voltage output over 0.016. So then we did this for the maximum voltage output we could get, 37.5 volts, and then the minimum rotor speed is 6.93 volts. Also, I think that should be AC. I'm sorry for that typo, but so we found that the range of speeds we could spin the testing generator at is 433 to 2,344 RPM. And here's just like another kind of graph to show how we kind of calculated that, or how they relate to each other. And then something else we did preliminary calculations for is the predicted power output we would have now that we know the range of speeds we can spin the generator at. So we know that the torque and rotational speed are inversely proportional due to their product equaling the power. And then we also know that the torque is limited by the maximum steady state current that the generator can handle due to heating issues. If the generator gets too hot, that would be kind of bad. So then what I was mentioning earlier when we said that we assumed the generator specs given was the max power outage is here on this point. And that's the maximum power at the greatest speed, rotor speed, before the power drops off. So that's the point we assumed. So then we wanted to at least have some predictions for the first few hundred RPMs of rotor speed that we spun. And so then we used the power equals torque times rotational speed equation to find the torque up until that greatest rotor speed. And we got that the torque was 2.55 Newton meters. So then that's just that red line right there. The torque is at 2.55 Newton meters from the 0 to the 750 RPM, which you will see in the next slide on the right. And then one more thing that we had to consider was that the controller wouldn't read voltage until 12 volts. And that corresponds to a 433 RPM speed. So we had to, so we kind of assumed that this, the power output would only start to linearly increase with the torque being 2.55 Newton meters after that minimum speed is reached, and the controllers are actually, accepting power, generating power, and charging the battery. So then for this last part with the drop off, we weren't given the specifications to calculate that part, so that might have to be verified through testing on the behavior of the power drop off after the 750 RPM. So here's just some more numbers that we predicted would come with the predicted out for the power output based on the rotor speed. So as you can see, the 433 is our minimum speed. And then we actually did notice at a based on our calculations from testing, we noticed that when the rotor speed was at 600 RPM, we saw a power output of 50 watts, which is pretty close to this prediction. But of course, we'll have to do more testing and research into how exactly and why exactly this is. And then basically the linearly increasing relationship, we shifted it to 433, and that was kind of our new zero. And then the 1183 is like the 750 in terms of the rotor speed and the power output. And then one final thing we did was to consider the wiring. So we calculated the current from the rectifier to controller and controller to battery load. The generator provided wires for the AC current coming out of them, so we assumed that the wires were designed to handle appropriate power and current outputs from the generator. So from the rectifier to controller, we found the current range from 3 amps to 16 amps, or around 16, 17 amps. And then the controller to battery is also at a maximum around 16, 17 amps. So we used a 12 gauge wire since it can handle up to 20 amps.
Yeah, so the purposes of those calculations were kind of just to make sure that we wouldn't burn out any of our components in the actual testing phase, and make sure that we keep our testing generator within its limits so as to keep everything safe. And also determine any potential sources of inefficiency if there were discrepancies between our theoretical calculations and what we end up finding in our tests. So while we're testing, we wanted to kind of determine 4 main aspects of our setup. The first is to determine that max RPM for safe controller operation. This is in like an actual application. This is to determine at what wind speeds would it become dangerous to have this setup. So the way we did this was we spun our generator at an arbitrary speed and counted the number of revolutions, or the amount of time it took to complete 10 revolutions. And we ended up finding that at a rotational speed of 85.7 RPM, we produced 2 volts AC, so from the generator to the rectifier, and that the rectifier converted that into 2.5 volts DC. Extrapolating this relationship, because it's proportional, we know that the controller max is 65 volts from its data sheet. We determined that the max RPM for safe operation would be 2228.2. The second thing we wanted to determine was the resistor wattage. So one thing we realized after we had gotten our components and assembled them was that the controller did not treat the dump load resistor as in the way that we wanted it to. So instead of only diverting power to the resistor when the battery was fully charged, or if there was any overcharge conditions, it would consistently pour power from the battery into the resistor. So this is not what we wanted, and it's something that we want to address moving forward and would have to be addressed before implementing this, because we never encountered a need for a dump load resistor, but we definitely expect there to be conditions in an actual site where we would need to have that safety feature. But realizing this, we also wanted to determine how effective this resistor was at dissipating any potential overcharge. So we knew that the battery was 12 volts, the resistor was rated at 1.5 ohms, and using the equation V over I equals A, we determined that 10 amps would be going through the resistor, which means that the resistor can dissipate 130 watts. The third thing we wanted to determine was where the battery would start charging. So when the controller would start diverting power and actually charge the battery, which is what we want. Because we realized that as we had predicted would happen, the controller won't charge the battery if it's under a certain, if the rectifier does not go up to a certain point. So to determine exactly which limit this was, we essentially just like tested the generator at different speeds until we got a reading of when the power was diverted to the battery. And we determined that point to be at 14.2 volts. So the reason why this is higher than the normal rated battery, which is 12 or I think like 13.8 volts, is because of inefficiencies in the form of a diode drop within the controller. So taking that difference between the like measured limit and the expected limit of the battery, we determined that the diode drop is about 1 volt through the controller. And the last thing we wanted to determine was where else there were inefficiencies in our system. So measuring diode drops across the rectifier as well. So between the rectifier and the controller, we were able to measure a diode drop of 0.64 volts. And between the AC pins on the rectifier to the DC pins, we were able to determine there was a diode drop of 0.416 volts. So this is kind of a understanding of the separation of inefficiencies because we have these separate parts as opposed to together in a single wind controller. Everything we determined in our testing. Yeah, we wanted to thank Rebecca and Nicholas for helping us along so much and giving us advice through our entire process. And thank you to GAIA and WindAid for organizing this event.
So here's our setup for our actual lab experiment. So as you can see, we have the generator hooked onto the rectifier, which goes to the controller, and then the battery, because we realized that the dump load resistor isn't working as we thought it would. So then right now, Nico is gonna spin a drill that will spin the generator. And then we should see, once he spins it fast enough, there will be wattage output on this controller's monitor right here. So I'm gonna press this button and it's gonna show the wattage, which is basically the amount of power that's going to the battery. As you can see on the symbol here, it's like from the generator going to the battery. So basically the battery is charging.
Can you hold it on the other way?
This way or this way?
Yeah, yeah.
Okay.
Okay, and then you can also observe the voltage readings on here from the rectifier outputs. So I guess should we spin? Okay, I'm gonna set it up. Okay, we're ready. Okay. We can see that there was a little bit of wattage output on this. So you can see the spin it faster again. Yes. And it's at 18 watts in this. And you can see that we're kind of staying within the upper range of 65 volts, but we are clearly under look at that. We are at 42 watts per minute. Okay. Yeah, that was okay.
So we will get started with the next technical presentation. This one, as I mentioned before, was originally included in the scope of the problem statement for another competitive team, the MIT team, but they were not able to finish the project. And so the GAIA organizer team is completing this project. And we are excited to show you our model calculation and results for the wind aid generator. So I will walk through the goals of this project and additionally some more technical details about the Peru trip that happened in January, where we aimed to characterize the existing generators. Then I will talk through the existing solutions in detail, go through our design process, our modeling as well as design optimization process, and then end with some future work for the generator system. Starting off with the goals. So as we mentioned in the previous presentation, the current wind aid generator has an efficiency of less than 50%, and it uses a pretty large amount of both magnetic material and copper. And so we wanted to optimize the power efficiency, the economic efficiency, while maintaining the level of manufacturability with an emphasis on locally sourced components from Trujillo, Peru. And in particular, on the power efficiency side, we want to make sure that the generator can match the amount of torque that the aerodynamics or the blades are capable of producing. And on the economic side, that is reducing the amount of magnetic material, which is, apart from the controller, the magnets are the only other piece of the turbine that cannot be sourced from Trujillo. The magnets have to come from Lima currently, in addition to the copper, which is the biggest single cost component on the generator. So here's some more technical details about the dynamometer setup in the January Peru trip. So there's a AC power supply, a transformer, in fact, that we use to power a induction motor. That is the green device. And then these are mechanically coupled through the shaft to the generator. The Laplace generator is the one shown in the picture. And the Laplace generator is generating into a controller. That's an MPPT controller. The competitive team talked a little about this. Is a maximum power point tracking controller that basically ensures that the optimal tip speed ratio, which is an aerodynamic parameter, is maintained on the turbine. And so what we wanted to do with this dynamometer setup is basically by putting the motor and the generator together, you're able to load the generator. And so it's an alternative to spinning it with a drill, like we just saw the demonstration of, but being able to put a lot more power into it to see how it operates and basically obtain the entire torque speed curve and efficiency map, which means the efficiency as a function of torque and speed. And some secondary objectives that we had were to characterize the static parameters. That would be, for example, the resistance and inductance of the winding, as well as the back EMF constant. And those are all parameters that we input into the model, which are necessary for benchmarking and validation purposes. And so here are some measurements shown that we took on the Peru trip. So we successfully were able to measure the back EMF constant by measuring the AC output voltage of the generator at various different rotational speeds to get a linear fit for the back EMF constant. And then separately, that second graph there shows a transient response of voltage over time on the winding. And this was in response to a step input, and the natural frequency and damping coefficient of this underdamped response allows us to characterize the winding impedance. So that is both the resistance and the imaginary component, the inductance of the winding. And so these were helpful pieces of data that we were able to measure on the Laplace generator in Peru that we can now use for benchmarking and validation. And unfortunately, some other measurements were not able to be accomplished on that trip. And so namely, the piece of data that we were most looking forward to gathering, the torque speed curve and efficiency map, we were not able to get. And one reason that initially prevented us from getting this was that the capacitor in the MPPT controller that we were using blew. And so initially we were unsure why this was happening, but we're able to trace it back to the back EMF constant of the Laplace generator being too high. And so what that means is that for a given rotational speed that is typical of something that the wind might spin the turbine at, the voltage that is produced on the generator is too high to a level that damages the controller. We measured more than 100 AC volts on the phase of the generator when the controller is designed to operate at a maximum of 48 volts. And so that resulted in a blown capacitor. And this is actually a really important learning point, because without this testing, we wouldn't have known that the back EMF constant of the Laplace generator was not suitable for the wind aid system. That basically it was not suitable to be used with a 12-volt battery system. And so that needs to be taken into account in the future when suggesting any design considerations, that even though the Laplace generator theoretically could produce twice the power, because its voltage was mismatched, in reality, it was not able to be very effective, and it broke the controller. And so we did have a spare MPPT controller. So after the broken capacitor, we were able to use that spare one, and still with that spare one, because of the controller being different than the typical controller that Wind Aid uses for their other turbines, we were unable to get that controller to actually absorb any power or operate at load. And it's still a little bit unclear why this was the case, but this prevented us from getting even torque speed data at low speed, which is all we could have done given the mismatch of the back EMF constant. And so these are measurements that, although we would have liked to have had, are things that we're still able to work around, given our validation of the static parameters in the model. And so existing solutions, I mentioned briefly the Laplace generator, and I want to go a little bit more in depth on this generator and its assumptions, and as well as other existing models before diving into our own model. So the most obvious existing solution is the standard generator design that Wind Aid has been using for years. And so this is based off of the Hugh Pigott turbine design. It is an axial flux machine that contains 8 magnets or 8 poles, and it is wound by hand, the copper coils, and the magnets are placed on a piece of steel. And here's a pie chart showing the cost breakdown of the current Wind Aid generator based on a bill of materials that Wind Aid has sent us. And you can see that the largest cost component is actually the copper, followed by an assortment of mechanical components like the shafts and the bearings and the screws, all of those small things that add up, as well as the magnets being other really big cost components. And the steel plate behind the magnets is not a particularly large cost component. And additionally, there is a zinc plating on the magnets that is used to protect them from corrosion. So in some sense, you could lump that into the magnets, but it is broken out. And so knowing this cost breakdown is helpful because it lets us know where is most important to target for cost reductions. And so the mechanical cost reductions, it's not very feasible to have mechanical cost reductions because those are all components that need to exist, and none of those individual components are very expensive, and the amount of torque should not change very substantially because we still want to be able to handle the full aerodynamic torque. And so that's why we're focusing on the magnets and the copper as the 2 primary areas of cost reduction for the generator. And so to analyze this in like an optimization, we need an electromagnetic model of the underlying equations so that we can know if we change what aspect of the design, what will be the effect on the overall operating parameters. And so the starting point that we had for this electromagnetic model was a model created by a engineering senior design team at Dartmouth about 6 years ago. And so we call this the Dartmouth model. They had a model that includes finite element analysis using the FEM, or finite element magnetic method, package. And so it also includes the aerodynamics. Basically, they input a curve for the blades, CP versus lambda, that's coefficient of performance versus tip speed ratio, and combines that with the more detailed electromagnetic model. And they were able to validate this model by taking a couple of experimental data points with a passive rectifier in their shop. And so it's helpful as a baseline. However, there are many drawbacks to the Dartmouth model that as we looked more into it, we found. And so one that is kind of glaring to us was there was unfortunately a factor of 4 error in the power caused by swapping the diameter of the blades with the radius of the blades. And so this meant that right off the bat, none of the conclusions could really be trusted, although that is a very simple thing to fix in the model. And as we dug even further into it, basically finding that the torque versus speed curve used did not seem to really align with our expectations. And so part of that is they're assuming passive rectification only, so basically a diode rectifier, and they're not assuming a active controller. And this can change the torque speed curve. Until very recently, we were not aware of that distinction of the different shapes of torque speed curves depending on the type of rectification. And so we're learning more about that in this process of modeling, and we'll hopefully be able to better evaluate exactly how we need to tweak the Dartmouth model to take that into account. But we can see the graph here shows the ultimate torque versus speed curve that the Dartmouth model produced. And they are predicting a power of only 25 watts for the generator, as well as an efficiency of 89%. And so these numbers really aren't matching up with, we know that the current wind generator is able to produce 240 watts of electrical power, and that its efficiency is, in one measurement, was around 47%. And so it is both overestimating the efficiency and drastically underestimating the power, even once you account for this factor of 4 error from the diameter and radius. And so we determined that this model, while it was helpful as a baseline, needed definitely a lot of work and further investigation before we could use it to make decisions to suggest to WindAid. The second existing piece of work that we had to go off of from the generator was the Laplace generator. So Laplace Laboratories is, I believe, a national lab located in France, and they worked with WindAid to design a new generator, hoping to take into account the drawbacks of the standard WindAid design. And so their generator is pictured there. There's one 3D printed version in white, and then one manufactured using realistic locally sourced materials like steel, or sorry, not steel, that's a composite on the right. And so the benefits of the Laplace generator, they use larger, stronger magnets. And so in particular, the original WindAid design used N42 strength magnets, whereas the Laplace generator uses N52 strength neodymium magnets. So that's basically the strongest there is. And there's also a substantially reduced air gap, basically meaning that you can get the magnet and the coils a lot closer together. And that increases the magnetic field through the air gap, which is one of the most important operating parameters for the torque of the system. And so because of those design changes, the theoretical capability of the Laplace generator is it can handle more than twice the power of the wind aid generator. And this is useful because it would allow operation of the entire torque speed curve that is aerodynamically possible. So we would no longer be generator limited. However, the biggest drawback with the Laplace generator is something that we found on the January Peru trip, that the back EMF constant is way too high. And at typical wind speeds, it would be producing 70 volts and is incompatible with most commercially available controllers. And that's a pretty major problem that will prevent even like integration and testing of this device. And so we are hoping to have a little bit more insight and discussion with the Laplace team in the future about whether this was a calculation error on their part or a misunderstanding of requirements, or where this discrepancy might have come from. Another interesting fact about the Laplace generator is that it does not use steel. And this is rather strange. So as we saw like 2 slides ago, the cost of steel in the wind aid turbine right now is less than 5% of the total cost. Steel is not a particularly rare raw material in the context of Peru, but the Laplace report that we read basically said that the designers were wanting to minimize and eliminate the use of steel because according to them, it was a more scarce material. And we have also asked Wind Aid about this, and they were kind of like, well, we don't really have a problem with using steel. And so we think that this was perhaps a miscommunicated design requirement that means that the generator could actually benefit from using steel again. That would make it able to use smaller magnets, perhaps even less copper, and be cheaper while still achieving the same levels of magnetic flux, because the steel helps to prevent flux leakage, leaking out of the generator. And because it uses primarily the bigger and more magnets, but also just overall construction-wise, the Laplace generator is 50% more expensive than the standard Wind Aid design. So it's in fact going in the wrong direction, although it does have more power. And so we were hoping to learn from the drawbacks of each of these previous design processes and these models to synthesize a recommended generator design that we could recommend to Wind Aid for the future. And so on the physics side, we looked at the coil, magnet, air gap, and steel. And so with the coil, on most standard motors in like machinery, they are wound using a machine. And that means that they're able to have a lot more flexibility in their winding design. However, because being locally manufactured is a really big priority for Wind Aid, their coils are wound by hand using like a machine with a crank on it. And so that places constraints on the dimensions, the number of turns, and the wire gauge that can reasonably be used in the coil. And the coil does not affect cost very much because the gauge of wire, it doesn't cost that much different between different gauges of wire, but it is a substantial contributor to cost, the overall amount of copper that is used. So in that sense, the coils do play an important role. And then on the air gap side, we already talked about minimizing air gap will increase the magnetic field through the air gap and therefore increase the torque of the machine, which leads to more power. However, on the flip side, having such a small air gap is a tolerance issue, which decreases the manufacturability. And so this is a constraint that requires a little bit more discussion and back and forth with Wind Aid about what level of tolerance is realistic in their workshop, and given their manufacturing techniques, that we could go down to a smaller air gap. And then additionally, the magnet properties. So the big difference between the Windade generator and the Laplace generator was the number, size, and strength of the magnets. And so our model accounts for all of these things. And then finally, the steel. We model steel in our electromagnetic model as an infinite permeability material, which is a little bit of an ideal assumption. But to mitigate the effect of this, we do limit the magnetic field through the steel to prevent saturation in it. And so with this physics-based simulation that we're able to build, we can test a whole bunch of different combinations, and ultimately we need some selection criteria. How are we going to decide from all the different possible generator designs which one we recommend? And so the criteria we ended up using is minimizing two different objectives, the mass of magnets and the mass of copper, because again, those were the two big cost contributors that are able to be changed by the design of the generator. And then a constraint of this process is that we need sufficient torque to basically allow as much torque as the aerodynamics as the blades are able to provide, up to a maximum wind speed of 10 meters per second, which is a largest typical wind speed in this part of Peru. And so given this selection criteria, we're able to incorporate the power efficiency with that constraint, basically enforcing the torque speed curve of the motor is always above what the blades can provide. And we use the coefficient of performance versus tip speed ratio curve. And that ensures that there's no power left on the table, so to speak. And then on the cost efficiency side, that's where the minimizing magnet and copper mass comes in. And by hopefully reducing the cost of the controller, it will allow Windade to produce more turbines. And of course, keeping the voltage low. We just basically include the DC voltage of 12 volts as a parameter in the optimization, so it's not even needed as a constraint. And finally, for manufacturability, we filter the designs based on achievable air gap and number of turns. And those are currently just estimates, but can be refined once we have further discussions about the manufacturability with Windade. So now I'll talk about the exact physics details of the model. So we have both a radial flux model and an axial flux model. These are two different types of generators or motors. Both of them are permanent magnet synchronous machines, but the direction of the flux in the magnetic field differs basically whether it is radial or axial, as the names would suggest. So for our radial flux model, radial flux machines are much more typical, and the Laplace machine is a radial flux machine. And so for the radial flux machine, we use a magnetic circuit model. Here's a diagram of that magnetic circuit where the permanent magnets are modeled as current sources, and then the different materials are modeled as reluctances, which are resistances to the flow of magnetic flux. And yeah, basically all of this analysis came from a very useful textbook by Professor Hanselman. And because it is all analytical, this means that it's able to run really fast. There's no numerical computation or like nonlinear equation solving that is required. And we're able to maintain some level of nonlinearity by using Fourier analysis. This basically composes a waveform into the fundamental and its higher harmonics. And we can see the effect and how much the motor diverges from the ideal sinusoidal motor. And with the steel, we calculate the thickness required to prevent saturation. And so the steel thickness is not a design variable, it's an output. And I'll contrast this with the axial flux model. Windade's existing machine is an axial flux machine, and therefore the Dartmouth model already has implemented an axial flux model that uses FEA, finite element analysis. And this is a more complex form of analysis. It lets you get greater detail, but it takes longer time. And And another, so some more detail that it gives you is it gives you a more detailed spatial resolution of the flux. You can see from this image, for example, how the flux paths go from magnet to magnet and then through the steel. And it also includes real material parameters. So we're not assuming infinite permeability of the steel for this. The steel has some finite permeability in its material parameters. And so the bare bones of the Dartmouth model, we're still able to use the way it sets up this finite element analysis in the FEM software. But the main things that we're modifying are after it computes this, what do you do with magnetic field to get the torque speed curve and the power? Those are the main things that we are changing. And so this is a piece, the systems model that I mentioned before is not created yet, but ultimately, instead of assuming that the generator needs to produce as much torque as aerodynamically possible, in the future, for example, it might make sense to have a co-optimization between the aerodynamics and the blade design and the generator design, or even just look at what would happen. Is it worthwhile to have a smaller generator that does not quite get the maximum aerodynamic torque, but still gets plenty? And so for this type of analysis, we would be integrating the systems model, which again consists of the physics model of all the different disciplines, as well as a battery charge model to ultimately give us the metric of how many hours per year the family who's using the wind turbine does not have access to electricity because their battery is dead. And so that will be an alternate objective in the future. And some detail on the systems model. Basically, we have interaction now between the torque and speed of the aerodynamics and the torque and speed of the generator. So the aerodynamic curves are shown in orange and pink there. Basically, this comes from the coefficient of performance versus lambda curve that gets scaled appropriately to find the aerodynamic torque and speed. And then the generator torque and speed capability is overlaid on that, and we can find what are the feasible operating regimes of these combined constraints. And given the overlap of these curves, we will change that, we'll transform that into a mechanical power as a function of wind speed curve that can then be used to look up based on the wind speed over time, hourly weather data, to get the average mechanical power, run that through the efficiency to get the average electrical power, and that will go through the battery model to charge our modeled battery and determine how many hours a year the battery is empty. And so here are some results of running this model. And so you can see that the rotor is shown in black and the stator is shown in red. The optimal generator that was output of this optimization right now contains 15 slots and 10 poles. It can produce 8 Newton meters peak. It has a top speed of around 1700 RPM and it weighs 4 kilograms. And you can also see the torque speed curve there. And to do further analysis on all the different generators that were tested, basically this optimization brute forced every possible combination of different generator designs of different magnet sizes and placements and number of coils and all that. And we can make a scatter plot of what's called a Pareto front to look at the two objectives that we care about minimizing, the magnet mass and the copper mass. And so the designs are marked in orange that have the best trade-off combination of these two. And one thing to note here is that there are very few of these orange points that are called non-dominated. And so it is worth like doing some additional analysis later to double check that that fully makes sense. Are we testing enough designs? Do we need to expand the range of the sweep, for example? And especially that the Pareto curve is rather steep, that like these orange dots form a roughly vertical line. whereas you might expect there to be more of like a gradual trade-off. And so that's the thing that we will be looking into in the future as well before we like officially recommend this to WindAid. But it is pretty promising that we're able to do this type of analysis for the radial flux machine. And also, if we know the per kilogram cost of magnetic material and of copper, we can plug those in to get an overall singular cost minimizing generator. So it would basically be picking from one of these orange points, which one makes sense based on the relative prices of magnets and copper. And so looking forwards on this project, based on the current optimization results, to minimize the total active mass, which is the sum of the copper and the magnetic mass, the trends that we observed from this optimization are to minimize a whole bunch of dimensions, which you would honestly expect because you want the materials to be as small as possible. And so everything is as small as it can within the constraint of having enough torque. And also the current results are showing that there is actually no relationship with the wire gauge, which would mean that the winding can be chosen pretty freely. That would be convenient if it is actually the case, but I'm a little bit suspicious of that result. And so we'll be looking into that further because I would expect there to be a relationship with the wire gauge. And so additional thing that we will be doing for this project going forward is resolving some confusion that recently came up with what the torque speed curve looks like for different types of rectifiers. I was mentioning active versus passive. So the active converter is what you would very standardly see as the torque speed curve of a motor or generator, where there's a pretty flat torque that is dominated by thermals. It's current limited, followed by, at higher speeds, a linear slope down that is voltage limited. And that's imposed because there is a fixed amount of voltage available from the converter. And the torque speed curve potentially looks a lot different for a passive rectifier. And this is analysis that we are still confirming whether it's correct or not, but basically because a passive converter is not able to create an arbitrary voltage at its terminals, it's only able to generate once the back EMF exceeds that voltage, for example, 12 volts for a 12-volt battery system. And that introduces some kind of weird thresholding behavior where there's a electromagnetic cut-in speed where you can't actually produce torque until the speed is high enough, as well as this kind of inverted shape of the torque speed curve. And so this will need to be better implemented into both the axial flux and the radial flux model. And so then we can compare them apples to apples and suggest overall what the best generator design is for the WindAid application. And here's a timeline outlining some of these next steps, including the systems model and finishing these refinements of the generator model in the month of May. Then moving into the summer, getting more specific about the detail design, starting to CAD the generator that is ultimately recommended, prototyping it in the fall to hopefully partner with WindAid to have documentation about it and start to build it and use it in turbines maybe like a year from now. And thank you. Are there any questions about the generator? I would next like to introduce AJ, who is on the international team, and he's going to give a great talk called Navigating Race and Identity Abroad.
All right, good afternoon, everyone. I'm sorry I had to miss most of demo day. I had a required orientation for my summer program I'm part of this summer, but I hope everything went well. So yeah, it's just quick show of hands. Who here has been abroad before in a different country? Okay, follow-up question to that for people who raise their hands. Did you notice any discomfort in terms of how you perceived, just economic disparities or how your race interplayed to the local, I guess, makeup of the area in any sense or no? Raise your hand if you felt that way. In a sense, a little bit? Okay, cool. So yeah, that's what we're gonna be talking about. Just when you're abroad, how you can navigate your identity and race in an unfamiliar setting. So a lot of the concepts we'll be talking about today came from, oh, sorry, come from this book, Beyond Guilt Trips, Mindful Travel in an Unequal World by Anu Tawernath. It's a great book. I did it for my independent study in global development, and it's just a really great commentary about how, like, just basically what we're going to be talking about today. So, and we will read example excerpts from her book. So yeah, so luggage we take with us, identity and advantage. So travelers often encounter cultural, racial, and economic differences while abroad, This can be unsettling and confusing. Just as the people who raised their hands showed, well, why do we feel like this? Two simple reasons: traveler's guilt and what is perceived as, Western privilege. So regardless of what your socioeconomic status is or races within regardless of your socioeconomic status or what your race is within the Western Hemisphere, just by innately being born in the Western, as you might put it, we're all innately privileged to a certain extent. So how do we deal with this when we're abroad, and how do we get over this guilt we might feel? So I'm gonna read this. I know this might be a little bit small for you guys, but I'm just gonna read along this example excerpt. So she says, imagine being a young traveler from a Western country, eager to explore a low-income nation. You arrive with good intentions, hoping to broaden your horizons and learn about the people and cultures different from your own. But as you step into this unfamiliar environment, you feel a mix of emotions: curiosity, confusion, and discomfort. You encounter situations that challenge your assumptions and force you to confront your privilege. Perhaps you witness poverty, inequality, or cultural practices that seem foreign or uncomfortable. You grapple with how to think and speak about these differences. In that moment, you realize that travel isn't just about adventure, it's also about accountability. It's about acknowledging your own baggage, quote unquote, where you come from, what you've been taught, and how much you have here. So I'll give this a moment just to kind of digest that. Okay. So what I took away from that is, discomfort actually is a good thing. By feeling discomfort in these unfamiliar settings, you're acknowledging a history of colonialism and oppression. So the way I like to put it is the goal while you're traveling abroad in a different country is we're not meant to eliminate the complexities and contradictions of travel in an unequal world, but instead we're meant to understand and address them. So this kind of ties into this first point here. We're acknowledging a history of it. So because of that, we're all born in the 21st century. And it's not our sole duty to eliminate the years and years of colonialism and oppression that have come before us. But instead, we can work to, mitigate it and acknowledge what it has become and anything we can do to basically work towards a more equal world. By doing this, we build genuine relationship across difference. Okay. So in Taranath's book, she shares stories from her past students who went to go travel abroad and, for different reasons, programs, etc. And she shares them in the book. So this is one of her stories about his name is Alex, and he was doing a study abroad in Nepal. And so we'll read this very quick story and see what we can take away from it. So Alex sat cross-legged on a cushion floor mat, sipping steaming chai. The tea house was refugee from the bustling streets outside, a place where locals and travelers converged, sharing stories and laughter. Across from Alex sat Rajan, a weathered man with eyes that held a lifetime of experiences. They had struck up a conversation about life, culture, and dreams. Rajan spoke in broken English, and Alex listened intently, trying to bridge the language gap. Tourists come and go, Rajan said, stirring his chai. They take photos, buy souvenirs, but do they truly see us? Alex leaned forward and said, "What do you mean?" Rajan's gaze shifted to the window, where prayer flags fluttered in the breeze. They see our poverty, our temples, our mountains, but they miss our resilience, our spirit. They don't see the stories etched into these ancient walls. Alex felt a pang of discomfort. Had they been guilty of this too? Had they overlooked the deeper layers of Nepal's beauty? Rajan continued, travel isn't about sightseeing. It's about seeing with the heart. It's about sitting there, sharing tea, and understanding each other. As the sun dipped behind the Himalayas, Alex realized that discomfort wasn't something to avoid. It was an invitation to listen, learn, and connect. They vowed to approach every encounter with openness, even when it stirred their own privilege. So I have these two discussion questions that we can talk about for about 3 to 4 minutes. So the first one is, how does discomfort enhance our travel experiences? Consider moments when you felt out of your comfort zone while traveling. What insights or connections did you gain from those experiences? And the second one is, where John emphasizes seeing with the heart. What does this mean to you? And how could we be moved beyond surface level interactions to truly engage with people from different cultures? Share an example from your own travels where you've practiced mindful connection. So with the people right next to you, take about 2 to 3 minutes to quickly discuss these questions. Good, how about you? All right, I'm gonna bring us back here. So would anyone like to share what they discussed? Yeah. Yeah, exactly. So whether that comfort zone be in terms of cross-cultural differences or socioeconomic differences, like how we saw before, if we engage in those conversations across those differences, then we can actually form genuine relationship. Any other insights? All right, I'll just go on to the second story I have for us. I know that one's hard to see too, but I'll be reading out loud. All right, so the setting for this one is navigating discomfort in India. So Maya, a college student from the United States, embarked on a study abroad program in India. She was eager to immerse herself in a vibrant culture, learn from locals, and explore historical sites. However, as days turned into weeks, Maya began to feel a mix of emotions: excitement, confusion, and discomfort. One day, while visiting a bustling market in Delhi, Maya encountered a street vendor selling colorful fabrics. She struck up a conversation with the vendor, who shared stories about his family, struggles, and dreams. Maya listened intently, but she couldn't shake off her feelings of unease. The vendor's reality was far removed from her own privileged upbringing, and she grappled with the guilt. As Maya continued her travels, she met other locals: a rickshaw driver, a temple priest, and a young girl selling flowers by the Ganges. Each encounter led an indelible mark on her. She witnessed poverty, caste discrimination, and gender inequality. This stark contrast between her life back home and the lives of these individuals weighed heavily on her conscience. Maya's discomfort grew, but she didn't shy away from it. Instead, she engaged in self-reflection. She questioned her assumptions about privilege and biases. She sought out conversations with fellow travelers, sharing her feelings of guilt and confusion. Together, they explored ways to bridge cultural gaps and learn from their discomfort. Over time, Maya realized that discomfort wasn't something to avoid. It was an opportunity for growth. She learned to listen without judgment, to acknowledge her privilege, and to engage in meaningful dialogue. Her discomfort transformed into empathy, and she began to an advocate for responsible travel. Maya's story reminds us that mindful travel isn't about escaping discomfort, it's about embracing it. By acknowledging our discomfort, we can build connections, challenge stereotypes, and contribute to a more equitable world. So we have these two discussion questions here. So how did Maya's discomfort impact her perception of cultural differences and privilege? Discuss instances where discomfort can serve as a catalyst for self-reflection and growth during travel. And number two, in what ways can travelers navigate discomfort without falling into guilt or avoidance? Share personal experiences or strategies for engaging with discomfort mindfully while fostering meaningful connections with locals. So we can take another 3 to 4 minutes to discuss these with our groups. All right, I'm gonna bring us back here. So does anyone want to share what they talked about? No. Yeah, so kind of like that kind of ties into the cultural values in a sense where, maybe in America it's very a lot more individualistic, whereas in a different culture that emphasizes, familialism or collectivism, that might be kind of a culture shock in a sense. Yeah. Anyone else? All right, yeah. So I think the main takeaways from, the two stories we saw were that, us as travelers from a more developed country in the grand scheme of, global countries around the world, we shouldn't have to feel bad about our privilege, but instead we should be actively acknowledging it and working towards forming meaningful connections with wherever we travel. So whether that be, cross-cultural, cross-socioeconomic, um, our innate privilege from coming from a developed country should not at least hinder us from what we're there to do in that country. So, case of Gaia, this will be, you guys who travel to Peru, you guys are there to install the wind turbines for these local communities. And whether you're engaging with these locals face to face or, you're working with the wind aid engineers themselves, you will encounter, cultural and economic shocks that you did not expect before, unless any of you have been to Peru before. Or no, okay. So yeah, since all of you guys first time in a new country, these are just things to be aware about and very key points to being a mindful, responsible traveler as a GAIA competitor. Okay, and that's all about all I had today. So yeah, thank you.
Thanks to AJ for that talk and to all of the other speakers today. And I'm going to now give the closing remarks as the last event in our demo day. And it looks like we will be wrapping up a little bit early, just so that you're aware of the timeline. So I'm going to give a summary of everything that we presented today, talk about GAIA's plans for the future, including the summer into next year and a longer term 5-year vision. Starting off with the event today. I hope that this event really epitomizes GAIA's mission. GAIA was founded to be all about impact. GAIA maximizes the positive impact for communities in need. Not just aiming for a positive impact, but really maximize like as big as possible. That's what maximize is. And we've been, all the events today have really showed how we are trying to like maximize things, consider all the options and see how much impact that we can make and how much we can help WindAid accomplish its mission of electrifying rural households in Peru. And then going back to the second part of the mission, by empowering college teams to go through the entire design process, conception, design, prototyping, and execution of these solutions for global sustainability. I'm really proud of the Cornell competitor team who has been able to get all the way here as like the first GAIA team to really engage in a demo day and be able to have a solution to the problem statement is really exciting. And I hope that we're able to continue empowering this team and other teams to have the same sort of impact. And so going back to, Katie was mentioning this a little bit in the opening speech, but GAIA has been around for a little bit more than 2 years now. me, along with Mark and Mohammed, co-founded it as part of the engineering leadership program in March 2022. Then that was our founding. A year later, we got our funding through winning the Uni and Maxine Powell Social Impact Award through the Engineering Innovation Competition. And that was a big step forward to enable us to start actually planning the trips. And then our successes in January of our first travel to Windade in Peru for the scoping trip, enabled by a $5,000 grant from the Einhorn Center. And then today marking a big milestone as our first demo day. And overall through, I'll go back here, through all of this, we have seen that it is really possible to take the needs of our NGO partner Windade, translate them into design requirements through the problem statement, and then work with students iteratively to figure out the best solution and end up with models and of course a working prototype, which is really exciting. And so thank you to everyone for accomplishing that work. Next, I'll talk about the summer plans. So as we had mentioned, the plan is to implement this system in phase 2 of the GAIA program in the month of August in the Windade workshop in Trujillo, Peru. But leading up to that, there are definitely some more things to do on both the technical and the operational side. And so our internal technology team, as well as we're continuing to work with the Cornell competitive team to finalize the system and be clear on exactly what the technical, the bill of materials, the technical scope, the plan of events for the trip, as well as figuring out the operations for that trip with our operations team. And so that will be ongoing through the next couple of weeks for organization and ultimately leading up to the trip in August. And an expected trip itinerary, which we can go more into detail about, and especially as we talk more with Gandhi and the other person who runs the hands-on part of the workshop at Windade is Senora Bell, working with them. Our trip itinerary consists of finalizing the local sourcing of the rectifier and controller, assembling the system and testing it on the bench with those real locally sourced parts to verify that they are working, installing the controller on a turbine for data collection purposes in the workshop in Trujillo, and that will serve to test a lot of the edge cases and failure cases that might only occur when the system is on a real wind turbine as opposed to on the bench. And then finally, getting it out into the field, pending Windade's other installation dates, and that would be really concretizing the impact of having this new and cheaper controller system that a family can really be using for their electricity needs. And then our plans for next year. So we will be updating the problem statement based on all that we learned from this year. So this year, the projects that were executed was the controller getting all the way to the prototype stage and the generator only in the modeling stage. And this year used qualitative metrics in the problem statement. Next year, we're hoping that by continuing to work with Windade, we'll be able to refine this even more to enable the co-design of different subsystems, including, for example, the controller, generator, energy storage like battery, and the blades. And then finally leveraging the system model that we've been planning to have the problem statement be really based around quantitative metrics so that design decisions can be made in a more logical and goal-oriented way is the goal for next year. A second goal for next year is to validate GAIA's operational model. And so I'll talk about 3 different aspects of GAIA's operational model and where we are on that. So as you know, GAIA is a relatively new a new organization. And one of the first hypotheses that we posited with defining GAIA was that college engineering students are a source of untapped potential for making impact. Hypothesizing that college students being eager to gain experience are willing to devote more time and energy than, for example, working engineers who would volunteer after hours, that colleges are a great place to have this sort of impact because colleges offer the monetary resources for prototyping and travel to help students do that, as well as technical guidance of mentors and professors, as even just peers and classmates. And finally, the existence of a gap in this operational model, a gap in this paradigm of impact for college engineers. Most existing engineering programs either focus on really rigorous engineering or having the global sustainability context, and there are pretty limited opportunities to do both. And that's what GAIA is really aiming to be, that intersection of having the rigorous engineering applied in this global sustainability context and using that to make the most impact possible. And so I think so far we have not observed any evidence that would negate this hypothesis, and it's still a thing that we will be refining in the coming year. The second piece of GAIA's operational model that we can validate next year once we finally have this first demo day under our belt is the structure of how GAIA works. And so we hypothesize that the best way to activate the untapped potential of college engineers for impact is to organize a yearly competition. Our motivation for this hypothesis is that students are really motivated by either competing or by learning. Those motivated by competing, it's kind of obvious that having competition will motivate them. Those motivated by learning will still be motivated by this competition because the best way to learn how to do something is to do it. And so by having this really hands-on impact-focused competition, that is the best way to learn how to have impact, is to really have impact and not to just think about how you would have impact. And that yearly competitions are a pretty proven structure that, especially at Cornell, the engineering project team ecosystem, but also at other universities, that will unify, energize, and focus engineering students towards this common goal. And one question that we have for this operational model that we'll be thinking about going into the future is avoiding the perceived conflict of interest related to, so us organizers are all Cornell students, and having competitors coming from different schools, including Cornell. And if we are to expand to multiple schools in the future, making sure that we're being very clear and fair about the way that we're interacting with all the different teams and being able to help everyone as much as possible. And so we've previously done this with some site visits to the MIT team earlier this year. And so we'll have to explore what that looks like as GAIA's scope grows and whether that is feasible or if there are other operational ways to do this. And a third piece of GAIA's operational model that we will be hoping to validate in the upcoming year is that our more detailed way of operating, that we hypothesize that new teams can successfully make progress on the problem statement when provided with technical resources, a suggested timeline, and weekly office hours. This hypothesis has been the one that we have struggled with, I think, the most out of the three as an organization. And so, as you're probably aware, we no longer have the MIT team competing with us. There were also other teams who were interested at the very beginning, who never really started on the project. And so we are really hoping to, now that we have like a competitive team who has really gotten through it, to talk more with you guys about like how the experience was for you and how it can be made better in the future. And looking at providing more support in addition to the technical side on like the leadership and operations side, or whether we want to prioritize making sure that competitor teams have an experienced engineer on the team who is able to guide on the technical side, different things like that, or even exploring mature organizational structures that would not require building an organization from scratch. For example, senior design projects or existing project teams, all things which GAIA as the organizers will be considering. And we are eager to make these operations as good as they can be for the success of teams and ultimately to be able to enable the most amount of impact. And then an additional plan for the coming year would be to potentially expand to other competitors. And so these are some schools who have previously showed interest in GAIA or schools that we have potential connections to. And so we'll be deciding over the summer the exact scope of how many competitive teams we are aiming to have for the next year, trying to balance the amount of impact that can be had with breadth, with also the depth of amount of support that we're able to give each team. And then I'll move on to a more long-term vision for GAIA. So ultimately, we envision for GAIA to really become big for maybe not in 5 years, but in 10, 15 years to be, you know, in every engineering college and to have like the same way that mature project teams like those from Society of Automotive Engineers, like Formula and Baja are, for there to be many teams, mature teams, helping teams to be more independent and leveraging their own forms of funding and organization, so that we can really have and like empower as much impact as possible. And on the partnership side, we hope to continue maintaining a long-term relationship with Windade, who has as our first partner been like great to work with. And then also in the longer term timescale, adding on new partners who work on other sustainable development goals. As you remember, so far we're only addressing sustainable development goal number 7, and there are 17, so 16 more for us to explore. And so as we continue to grow in the future, it will be important to strategically look at all aspects of global sustainability and not just wind power. And I will finally conclude that the future is in our hands, that we are all here in this room because we care about impact and we care about achieving GAIA's mission. And I hope that this demo day has served to inspire and excite and empower all of you to be able to make an impact through GAIA and through any other endeavors that you do. And so I'll wrap up by giving a very warm thank you to all of the different organizations who helped us get to this point. Our community partner, the Windade Institute, the Cornell Engineering Leadership Program, who we were founded out of and who has continued to provide us organizational and leadership support. The Einhorn Center and the Engineering Innovation Competition, who have funded GAIA. The Engineering Project Teams Office, who helped make the trip to Peru in January possible. The Cornell Maker Club, who we have used the facilities and materials of for the testing of the prototype. And then finally, the C Lab, which is my lab, who we have leveraged the generator model of, which is also like my generator model, and who we have borrowed an M8 socket adapter from. And so thank you to everyone to all of these organizations, and GAIA would not be where we are without all of these organizations. And thank you.